Yes.
Okay. Okay, welcome everyone to the Monday afternoon session. Today we will have one talk followed by a 10-minute break, and then we will have a problem session. This is your opportunity to tell us your problems. And I will be inviting speakers to the board so that we can hear you properly across the whole room. And I'll be handing you the mic and also limiting your time to 5 minutes each. But I want to encourage a little bit of discussion with each problem statement so that we have some motivation to continue working on these. So with that, I have the great pleasure of introducing Prahlad Sharma from Max Planck, who will speak to us today about Sub-Weyl bound for GL2L functions.
Thank you, Roman. Thank you for the introduction, and thank you organizers for this nice conference. So I'll be talking about a new bound for GL2L function in the T aspect, which is obtained in a surprisingly elementary fashion. But let me start with a bit of a history about the problem we're going to look. So the story started around 100 years ago when Harding-Littlewood claimed that zeta at the critical line at height t is bounded by t power 1/6. So, but this was not formally written down by Harding-Littlewood. It was communicated to Landau, who finally wrote it down. So this basically used what is now known as the Weyl differentiation technique to estimate this exponential sum non-trivially. Okay, so since then many improvements over this bound have been achieved, giving rise to many important tools and techniques for estimating exponential sums in general. So I'll mention some of them. One of them is the following breakthrough bound of Bombay H. So they were able to beat the Weyl exponent. So this exponent is called, we call Weyl exponent. He was able to, they were able to beat this by this exponent 1 by 168. And so they used a mixture of all the three standard techniques available to estimate exponential sums. So these are the Weyl differencing, Ramanujan method, and the Van der Waals bound. And this was subsequently improved by Huxley, and he kind of did some refinement to their arguments and arrived at this better exponent, which is bigger than this. Okay, so these are all examples of what is known as the subcomplexity bound. Yeah, and the best bound we know for the zeta function is this bound by Bourgain. So he was able to get the exponent to 1 by 6 minus 1 by 84, and he uses this famous decoupling method coming from harmonic analysis. So that's the best we know for zeta. So these are all part of a bigger problem called the subcomplexity problem of L functions. So I'll very quickly go define it. So if you consider this Dirichlet series associated to some interesting arithmetic objects lambda f n, then this usually satisfies a Riemann type functional equation. So we have this, if you take this completed L function where this QF is the conductor, you have the product over the gamma factors, and this kappa i's are the Langlands parameter, and so this completed L function satisfies this relation, relating its value from 1 to 1 minus s. So the right hand side also has this root number associated to f. So once we know this functional equation, then we can, and if you define this analytic conductor to be the product of all the parameters appearing in the completed L function, then just by using this Frank-Lindelof convexity principle, along with the functional equation, you can have this bound which is 1/4 of the analytic conductor. So this is what we call the convexity bound, and a subconvexity bound is any improvement over this exponent 1/4, and a while bound we mean a bound which is 1/6 of the analytic conductor. So this is much more stronger than just any subconvexity bound. So I think we all have seen, we all know there are many important applications of various subconvexity bounds, but I will not go into those, but more importantly, they are solid testing ground for the current tools and techniques in the literature, and also they usually give rise to new techniques. Okay, so what we have just seen are examples for GL1 L functions in the T aspect. Let us try to see what we know for higher degree L functions. So for GL2 in the T aspect, this was first proved by Anton Good. So he also got this while bound, which is 1/6 of the conductor, which is T square in this case. So he deduced this by evaluating a mean square of the central L value, and then he reduced it to some sums of Kloosterman sum, and then he used the GL2 spectral theory to arrive at this bound. Okay, so there are many generalization of this bound and many other aspects, but I'll just focus on the T aspect in this talk. But I want to mention this famous work of Mishal and Venkatesh. So if you, they prove subconvexity for GL2 uniformly in all aspects. So as far as just the subconvexity bound is concerned, so this is completely solved. And this was based on viewing the cell function as periods. Okay, so that's what we know for GL2. For GL3, the first subconvexity bound was obtained by Xiaoqin Li, but she needed this crucial assumption of self-duality. This was because she was evaluating a first moment of this central L value, and if you want to deduce an upper bound, you need positivity of the central value, and hence you need this self-duality. And few years later, Ritabrata, he introduced the delta symbol approach for subconvexity problem in higher degrees, and his so this was so using the delta method, he was able to obtain subconvexity for a general SL3G forms. So there is no such assumptions in this case. So in this, he used what is called the GL2 delta method. So this is basically using the GL2 harmonics coming from the Peterson trace formula as a delta symbol. So after this, many subsequent works were done using the delta method approach for higher degree L functions, and I'll mention some of them. So one of them is the work by Keshav and Saurabh. So they recovered the GL2 while bound in the T aspect using the Kloosterman's delta method. And then we also have the work of Acharya Kumar, Mehti and Singh, where they also recover the while bound for the GL2 in the T aspect using the GL2 delta method that Ritabrata used for in this case. And meanwhile, Roman and his group, they realized that you don't actually, as far as the GL2 problem is concerned, you don't really need this high level machinery of GL2 harmonics. You just need a bunch of additive characters. So one of such examples was given by Keshav, who once again recovered the best known P aspect bound for GL2 using what is called the trivial delta method. So this is what we will also be using. Okay, so if you go higher, we have following subconstant bound for GL3 cross GL2 in the T aspect by Ritabrata, but now in this case he used the DFI's delta method. And we also have this nice result of Bloomer, Jar and Nelson, who so they got the Weyl bound for this triple product GL2 L functions. So this was based on the period integral approach, and of course we have the very recent result of Nelson, which solves the subconnexity problem in the T aspect for all degrees. So this was also is based on the period integral approach. Okay, so that's what we know in the T aspect. So to summarize, the best we know beyond GL1 is the Weyl bound, and that's also just for GL2. So for GL2 we know Weyl, and then for GL3 of course we are GL3 and higher, we are far away from Weyl. So so in this work we were able to break this barrier in the GL2 case. So we will use some refinement of the trivial delta method and get a improvement over the Weyl bound for the GL2 in the T aspect. So here F can be holomorphic mass form or just the Einstein series. So this our proof doesn't really see where F is coming from. Yeah, so this exponent should not be taken so seriously right now. So our priority right now is just to have some positive exponents. The extent to which we can push this work and obtain better exponent will be explored in. Yeah, this is pretty close to program. Yeah. But yeah, this changes every day. So, yeah. But yeah, I think with more effort, one can really get very good bounds. Yeah. So let me just directly go into the sketch of the proof. So as usual, we start with the approximate functional equation, which reduces your central value to this sums of dyadic sum Sn, which is sum over n lambda n twisted by n power it, and this capital N can go from 1 to capital T. And the estimate of this Sn is different depending on the size of n, as we will see. But right now, if you just bound absolute everything trivially, put absolute values, then you recover the convexity bound. So, so for Sub-Weyl, just to recall, you need the right hand side to be something less than t power 1/3. So, in other words, we need to show that Sn is bounded by root n times t power 1/3 minus some delta, some positive delta. So this has to be true for each n going from 1 to capital T. Okay. So the basic tool that we will use to analyze this sum Sn is the delta symbol. So this delta symbol will allow us to break our problem into smaller pieces at the cost of introducing more variables. And we usually hope to gain in overall structure of the sum, which would allow us to recover whatever we have lost plus something more. So this is the, let me define the delta symbol. So this is just 1 for the entry is 0 and 0 otherwise. So if you use this, you can rewrite Sn as 2 copies of m and n, lambda n, twisted by n power minus it, which are connected by this delta symbol. So you see, we started from 1 copies and now have 2 copies. So So before substituting an expansion for this delta symbol, we try to be less wasteful by doing the following step. So, we ask that m minus n not to be bigger than n. So we ask that m minus n should be something less than n. So say n by capital K, where this parameter will be chosen optimally at the end. And we detect this using this integral. So this is this integral will more or less say that m minus n has to be less than n by k, or else this is negligibly small. Okay, so yeah, so we try to gain. I mean, we try to be less wasteful by asking m minus n to be restricted by this. So this will be translated when we have cancellation from this V integral. This also acts as a conductor lowering device, as you might have seen, but and that is because since now you are detecting an equation of smaller size, the conductor arising from the delta symbol expansion will also be smaller. But in this case, the size of the conductor really doesn't matter for us, as you will see. So that is not so relevant here. But yeah, in other works, this also acts as a conductor lowering device. Okay, so we have this sum, we have this restriction. Now next step is to substitute a Fourier expansion for this delta symbol. So we use the most simplest version you can think of. So that is just the fact that any divisor of a positive integer has to be less than the integer itself. So in other words, if there is a divisor which is bigger than an integer k, then k has to be 0, and that's how we detect. So we can detect this congruence condition using this bunch of additive characters, and here we require that this modulus to be bigger than k. So it turns out this is all we need to get Sub-Weyl. Of course, you can also have this extra average over the moduli, which were used in previous work to obtain Weyl bounds, but we will see we don't really need this average as well. Okay, so we choose. So since our size of this k is capital N by capital K, we have to choose our modulus to be at least this. And then if p is bigger than this, we have the following delta symbol expansion. And we substitute this expansion in our sum. So after you substitute, the GL2 and the GL1 variable gets separated, and they look like this. We have the V integral, the B mod P sum coming from the delta symbol expansion, the GL2 sum twisted by this additive character and this analytic twist, and we have the GL1 sum with this additive character twisted by n power minus I t plus v. In the next step, we dualize this GL2 and GL1 sum using their functional equation. So for this GL2 sum, we apply the Voronoi summation formula, and we will land in this dual side. So the new length, dual length, will be of size p squared k squared by n. So this is usually the conductor size of the conductor divided by the initial length. So the conductor here in this case is p squared times k squared. So p squared k squared by n. And the additive character here, the b becomes b bar, and also the analytic twist becomes its conjugate m power minus iv. And we also have this normalizing factors. Similarly, we apply the Poisson summation formula for this n sum and arrive at the following dual sum. In this case, the length is pt by n. So pt is the conductor of the sum, n is the initial length. And since it's an additive character, the character sum boils down to this congruence condition. And now we substitute this transformation and arrive at the following. So we have this normalizing factors, the dual GL2 sum, dual GN1 sum. Now the character, the final character gets transformed into this additive character E of n bar m by p, and we have this twist by n by p power it. Also we have another analytic twist E of phi, where phi will be important to us. So phi roughly looks like this. So in terms of size, each lower order term is decreasing by a factor of k by t. So the leading oscillation here comes from this first term, and then we have the remaining terms. So recall that we will choose k to be some quantity less than t. So these are really low order terms, and we are ignoring the terms from the fourth because the size of the choice of k will be less than t power 3 by 4. So hence the remaining term are really flat. So we can ignore those. And if we try to see where are we at this stage, then you put absolute values everywhere and then multiply this lengths, and you arrive at this quantity. So the trivial bound, the bound we started was n, and now we have arrived at this n times this extra factor. So we are this factor away from the trivial bound n, and the power of p is will be important. I'll come back to this. So okay, so till now we have we haven't done anything new. So this was the same as the previous works, and it is at this step we will be doing some refinement. But before that, let me just quickly show how we get the Weyl bound from this. So we use the remaining variable by applying Cauchy-Schwarz inequality. So you take the GL2 variable outside the absolute value square and then put everything else inside the absolute value square. And here, if you note, this we have here we have an extra average over the moduli. This is because we need to recover this loss of in terms of p. We need to recover this p in the next step. So you really need this extra average to get to recover this power p from the diagonal. Okay, so we open up the diagonal, open up the absolute value square, and then execute the m sum using Poisson summation. Diagonal will be of size p times p into t by n, so p square t by n times the m length here. So in the diagonal we will not have any cancellation, so the whole length here, and in the off diagonal the m sum can be bounded by square root of k. So this is just a consequence of Poisson summation. And so usually one would have, so in presence of this arithmetic conductor p, one would have expected this to be square root of k times square root of p1 into square root of p2, p1 p2 being two copies of this sum. But since this is an additive character, the character sum boils down to a congruence condition, and hence we save more than the expected square root cancellation from the character sum, and that's why there is no p1 p2 here. Okay, so this is it. We substitute this bound from the diagonal. By diagonal value of size, so if you take square root of n out, we have this in the diagonal, and the off diagonal contribution is of size square root of t by k power 1/4. And now if you optimally choose k to balance the diagonal and the off diagonal, then the choice for k is t power 2 by 3, which you see that we arrive at exactly the Weyl bound. Okay, So as I said, we will be doing the refinement just before the Cauchy-Schwarz step. So what we will do is reduce the overall conductor of the GL2 sum here, and we do that in the following way. So we will approximate this number n bar by p appearing in this additive character here by another rational number a by q with and also this comes with the error beta, where beta is of size 1 by q square roughly. So the q, of course, we would like to choose q as small as possible to make the arithmetic conductor smaller, but then this will come with a analytic conductor beta. So you choose q to be the smallest number, such that the error coming from the analytic conductor does not dominate whatever we already have. So phi, if you remember, this has size k. So if we ask m beta to be at most of size k, then this will mean that q, you can take q to be this quantity, p times square root over k by n. And we will choose k to be strictly less than n. So this means that this q is really less than p. And this does so the analytic part remains the same. So the phi here still dominates m beta here. This means that we have kind of reduced overall conductor of the GL2 sum. So this is kind of another way of looking at your initial sum. So we started with a sum of conductor p squared times k squared, and now we have a sum of conductor q squared times k squared, and here q is strictly less than p. Okay, so we have broken the symmetry here, and now we apply Voronoi once more, since we have reduced the conductor as well. It makes sense. If you apply Voronoi once again, you will arrive at the following sum, where now the dual length is of size capital K. The additive character here becomes E of A bar m by p, and you have this transform of your analytic twist here. So this I will be the Hankel transform of this analytic twist, and this, to remind you, this is still of size capital K. The phase is of size capital K. Okay, so we put everything together and we arrive at the following final sum. This will again be important. This is still additive with respect to m modulo q. So just to check the status, we estimate everything trivially, and now if you see, we are just at the boundary. So this will just give the convexity boundary. So this is one difference from the earlier approach. So if you recall, in the earlier work, we were away from the boundary by this quantity, which had this factor of p with it. So we needed to take care of this factor p in the diagonal, but now there is no factor p that we need to take care about. So this is why we don't really need the extra average over the modeling. Okay, so next we do the usual thing. We apply Cauchy-Schwarz with the GL2 variable outside, and now in the inside the absolute value, we just have your dual GL1 length. Okay, so this is the usual diagonal contribution. So whatever is inside the diagonal times this sum over k. And in the off diagonal, once again, you apply a Poisson summation, and you can bound the n sum by a square root of k. This is because this I oscillates like k. But again, so there is this, since this is an additive character, the character sum will give a congruence condition, and hence you don't see the arithmetic modulus here, so you just get the square root of the analytic conductor here. Okay, so if you put everything together now and see where we are, then we'll arrive at the following bound. So you take square root of n outside. So this diagonal contribution is now square root of n by square root of p, and we have the off diagonal contribution, which is same as what we had earlier. So now, since p, we are free to choose, since this p is in the denominator, we are free to choose p as large as possible. So this main diagonal really goes away. So hence the bound is really comes from this. So for Sub-Weyl you just need to choose k to be anything bigger than t power to third. But we would like to choose, of course, k as large as possible. We would like to choose k to be at least t. But there are some barriers to that, and I'll quickly show you that. So there are two obstacles. One of them is technical, and the other is kind of a fundamental barrier. So the technical part is the following. So we got rid of the main off diagonal, but there still is some diagonal coming from the non-zero frequency as well. So if you look at the final transform sum that you get after applying Poisson summation, then you have this following dual sum n, which goes up to q1 q2, but as I said, you will get a congruence condition like this, and you have the dual GL1 sums from earlier, twisted by this transform, this correlation between our transform I. Okay, so the problem is one usually expects square root cancellation from this integral, but it might happen that the phases cancel out each other, and in that case we just hope to save the count in the count of n1 and n2 in those cases. But of course this, as I was telling you, these i's are made up of, they look like geometric series, so they are made up of terms, and each jth term is of size t by k power j. So if you analyze this counting problem up to this j term, then you will just save exactly t by k power j instead of the expected square root cancellation. So you see, if you choose k to be close to t, you don't really save from this counting. So this is one of the thing. But of course, you can keep analyzing your counting problem, taking into consideration more lower order terms. So in principle, this can we can really choose k to be close to t. But yeah, this will require work. But okay, but for Sub-Weyl, we just need to consider the counting problem for j equal to 2. And the counting problem that we arrived looks like the following. So this is approximating rational by cube root of rationals. Yeah, and we have, I mean, this is just an elementary exercise in yeah, this is just an elementary exercise. So this x square is the diagonal contribution when a and b are equal, c and d are equal, and you have the off diagonal contribution x4 times this quantity z. This is what we need for just for Sub-Weyl. Okay, I mean, if you consider more terms here, you will get more counting problems like this. But so in principle, it looks like this can be still done. But the fundamental problem choosing k to be large is the following. So if we really need to choose k to be less than n in order to activate the Diophantine approximation. So if you recall, we approximated this rational number n bar by p with a by q, where capital Q is of size p into square root of k by n. So if k is allowed to be bigger than n, then one has this trivial choice of q to be p, a to be n bar, and beta to be 0. So in this case, this does not do anything. So which is why we really need to choose k to be less than n, in which case you can see that q is strictly less than p, and beta also has this nice restriction. So it has this lower bound, which is 1 by q into p. Okay, so if you take this into consideration, we cannot really choose k to be very large. We have to be happy with k at most n. So you get the following bound, and here you see this is Sub-Weyl only when n is slightly bigger than 2/3. So all this really works only in this range. So what do we do in this boundary case n equals to 2 by 3? If n is slightly less than 2 by 3, then if you can use the trivial bound, that's enough to get Sub-Weyl. So the important case is when n equals to 2 by 3. So in this case, k is roughly n, which is 2 by 3. So there are two options to handle this. So the first is to push whatever you are doing in the following way. So in the final transform sum, we try to use this cancellation from these variables as well. But of course, this n1, n2 are involved in this congruence condition. So this is not so simple. Just to remind you, this ai and qi are functions of n1 and n2. Yeah, so we use these variables in the following way. So if you look at this definite approximation that we did, then this ai's, qi's, and beta I only depend on the residue classes mod p. Yeah, they only depend on ni modulo p. So if you restrict ni to be in a n1 and n2 to be in a fixed residue class, then we have some free variables at our disposal. So if you write ni to be some li mod p and write ni in this arithmetic progressions, then since ni is of size pt by n, this lambda i's will be of size t by n. But since n is small, n is like t power 2 by 3, we have some length remaining here. And these are kind of free variables from the congruence condition. So since we have this length, we can try to get some cancellation here. But let's try to check the analytic, let's try to compare this length with the analytic oscillation here. So this was of size k, this phase was of size k 2 by 3, and the length is of 1 by 3. So this is exactly the square root of the length. The length is square root of the conductor. So you can use Van der Korput's maybe third derivative bound to have a non-trivial estimate for this lambda 1. So even one non-trivial estimation is sufficient for us, but I guess we can also do both sums. But this would of course require we need to have asymptotics for this integral. So there are complicated stress interface analysis arguments which involves this new variables from the Diophantine approximation, beta i's, qi's. So this is a bit involved. The more simpler way is to go back to the previous approach. So we don't do Diophantine approximation. We do the usual Cauchy-Schwarz and look at the final transform sum here. So in this case, the final sum after Poisson summation will look like this. You have the dual sum will be of length n by k. So k will be very near to n for us. So this m is just like 1. And of course, in this case, you need this average over moduli as well. And you have this GL1 sums. So once again, we try to do the same thing. We try to use these variables non-trivially. So, and you can really do this because this congruence condition is, this only depends on n1 modulo p1 and n2 modulo p2. So, if you fix residue classes, you have this once again free variables lambda I, which is free from the congruence condition, and once again the length, the remaining length is of size roughly t power 1/3. The analytic phase here is of size 2/3. So, this is again we are in the same range. So, the length is square root of the conductor, and here again you can use van der Purpur's bound to estimate one or two of them non-trivially. So, but in this case I mean this phi we know what this phi really look like. So, these are much simpler to analyze. So, yeah, so I think, but the bounds from the both approaches are same. I mean, we will get the same savings. Yeah, so this is the end of my talk.
Prahlad. Questions for Prahlad?
On how far you can stretch the error, like can you get to Bourgain, or are there any fundamental reasons for
no, there are no fundamental reasons as of now that we cannot, we have not yet completely ruled out the possibility of beating Bourgain.
In the final case, when n is 2/3, t to the 2/3, so the paper of Roman, Munshi, and Jichi, so they are kind of getting Sub-Weyl type cancellation in this range, right?
Yeah, we can also directly use their result.
Yeah, you can do that, but the bound won't be that good, right?
No, I think he has.
It is same.
Yeah, but it's better. I think it will be better than this, of course.
Yeah, here if you can use third derivative bound, because there you are applying some exponent pair.
Yeah, he uses both these variables.
Yeah, two-dimensional exponent pair. Okay.
So have you thought about whether it would be possible to use decoupling in this problem?
Decoupling?
Yeah.
Oh, I don't have any idea. Oh, decoupling, I don't know.
Any other questions? Okay, let's thank Prahlad again.
Thank you.